Very good morning, students. In today's class, we are going to learn about the other properties of DFT. So, the sixth property of DFT is circular convolution in time. So far, you have learned the properties such as periodicity, linearity, circular time shift, circular frequency shift, and symmetry. So, the next property is circular convolution in time. So what is circular convolution property states? So let us have two different sequences x of n and h of n whose length be capital N. So then y of n is equal to x of n circular convolute h of n. That is, I am going to make the circular convolution between two time domain sequences x of n and h of n whose length is capital N. So if that is the case, using the circular convolution, I can write x of n circular convolute h of n as summation m is equal to 0 to n minus 1 x of n minus m with circular shift n into h of m. Or we can write it as summation m is equal to 0 to n minus 1 x of m, whereas the shift will be in the other one, that is h of n minus m with circular shift n. So hence you are going to prove this circular convolution property. So what is the DFT of this circular convoluted sequence? We are going to verify. So in order to prove this, I am going to have a block diagram as shown below. So what the block diagram says? So you have two different sequences x of n and h of n. I am going to take the DFT of x of n and h of n respectively as x of k and h of k. Then this x of k and h of k, it is multiplied and the result is written as y of k, which is nothing but the multiplication of x of k into h of k. Then I am going to give it to an IDFT block to get the sequence y of n. That is, IDFT of y of k will be y of n. So this is my block diagram. Using this block diagram, I am going to prove the circular convolution property of DFT. So from the above diagram, I can write y of k is equal to x of k into h of k. And what is y of n? Y of n is nothing but the IDFT of y of k. So we can write y of n is equal to the IDFT of y of k, which is IDFT of x of k into h of k. And as we know, the IDFT expression is 1 by n summation k is equal to 0 to n minus 1, the sequence x of k into h of k into wn power of minus kn. That is, the IDFT expression is given there, where that is x of k is equal to summation I is equal to 0 to n minus 1 x of I wn power of I into k, where k ranges from 0 to n minus 1. And we know h of k can be written as DFT of h of m. So h of k is equal to summation m is equal to 0 to n minus 1 h of m into wn power of m into k. And these two equations I am going to multiply and it is substituted in equation A. So what is equation A is? Here I have represented as equation A y of n and another equation x of k as equation 1. So this equation 1 x of k expression I am going to substitute in A equation. So thereby I am going to write y of n is equal to 1 by n summation k is equal to 0 to n minus 1 summation I is equal to 0 to n minus 1 x of I wn power of ik. So this is the expression for x of k multiplied by h of k, whereas instead of h of k we are taken as summation equation 2, that is summation m is equal to 0 to n minus 1 h of n wn power of mk into wn power of minus kn. So again, in order to get the proof, I am just interchanging the summations. So by interchanging the order of summations, that is the I is equal to 0 summation, I am going to write it first. So it becomes y of n is equal to 1 by n summation. Instead of k I am interchanging, I am writing I summation. So it is summation I is equal to 0 to n minus 1 along with x of I. Then the summation m is equal to 0 to n minus 1 h of n, and again the summation k is equal to 0 to n minus 1 multiplied with the wn power of, since wn is common, I am taking as wn power of I plus m minus n whole multiplied with k. So where I is equal to n minus m, and the summation I am going to equal to the summation over k equals n and 0 for other values of I. Hence I can write y of n is equal to 1 by n summation m is equal to 0 to m minus 1 n minus 1 x of n minus m into h of m multiplied by n. And finally we are getting the equation y of n is equal to summation m is equal to 0 to n minus 1 x of n minus m into h of m. So here what happens is the shift is circular, hence we can write y of n is equal to summation m is equal to 0 to n minus 1 x of n minus m with circular shift n multiplied with h of m. Hence finally if you see the expression on the right hand side, it is nothing but the circular convolution between two sequences x and h. Hence it is written as y of n is equal to x of n circular convolute h of n. Hence we have proved the circular convolution property of DFT. And you may get a doubt like where I is equal to n minus m, the complete summation value it becomes n, and it is 0 for all other values of I, hence it is equal to n. So again we have simplified, we are getting the final expression for circular convolution property as x of n circular convolute h of n. There is another subdivision of circular convolution property, which is circular convolution in time domain is equivalent to multiplication in frequency domain. That is, the DFT of x of n circular convolute h of n, it is equal to the multiplication between x of k and h of k. So this can be proved as DFT of x of n circular convolute h of n is equal to, that is I am going to take DFT of the circular convoluted sequences. So as per the circular convolution statement, I can replace this x of n circular convolute h of n as summation n is equal to 0 to n minus 1 x of l h of n minus l with circular shift n. That is with the help of circular convolution, that is convolution sum formula I have replaced here. And in the next step I am going to take DFT of this. So taking DFT of this, it is applicable only for h of n minus l with circular shift n, and I can write the expression as summation l is equal to 0 to n minus 1 x of l, whereas the DFT of h of n minus l with circular shift n can be written as capital H of k into wn power of kl. That is using the circular time shift property of DFT. As already you have studied the circular time shifting property of DFT, which is the circular shift of x of n with respect to capital N is equal to x of k into wn power of k into l. So using that property I have utilized here. So hence the right hand side expression becomes summation l is equal to 0 to n minus 1 x of l into wn power of kl into h of k. Then rearranging this so that I can write the first expression as x of k. That is, I just interchange h of k and wn power of kl, and the final expression is summation l is equal to 0 to n minus 1 x of l wn power of kl multiplied with h of k. So the first term, if you observe, it is nothing but the DFT of the sequence x of n, which can be written as x of k. Hence, the expression becomes x of k into h of k.